Hello and welcome to today's class. For today's fluid mechanics class, we're discussing about a very important topic in fluid mechanics as a course called flow rate. So let's discuss about the concept behind flow rate. When it comes to flow rate is simply the rate at which something comes out. So when it comes to flow rate, the rate at which something comes out. And when it comes to the idea of rate in science, when we say rate is simply a time bound word, right? So if I'm saying the rate of change of velocity, that's what the velocity over time, which is what acceleration. So if I mean the word rate of change, it means that a parameter is changing with respect to what? To time. So we're talking about the concept of flow rate. So what's flow rate? The rate at which something comes out is like the simple form of flow rate. When it comes to flow rate, there are two type of flow rate. We have the rate at which mass comes out. That one is called mass flow rate. We have the rate at which volume comes out. That's what volume flow rate, also called discharge. At this point here, let us discuss something important called type of flow rate. Type of flow rate. When it comes to discussing the types of flow rate, there are about two types of flow rate. Number one, we have what we call the mass flow rate. We have the mass flow rate, and number two there we have what we call the volume flow rate. These are the two distinct types of flow rate that we have. We have the mass flow rate and we have the volume flow rate. Let us talk about this flow rate one after the other. What's the definition behind mass flow rate? Let's start with mass flow rate. Definition: mass flow rate. This is simply the total quantity of mass of a fluid that flows in a particular time. So the total mass of a fluid that flow in a particular time is said to be what? Mass flow rate. It is represented by m dot. Is represented by m dot. So I'm saying that the symbol for representing mass flow rate is simply what? The m dot. Mathematically, mass flow rate is equal to, we said that's mass all over time. This becomes a mathematical expression, or perhaps the formula for calculating mass flow rate. So mass flow rate, which is m dot, is equal to what? Total mass all over time. So I'm saying that mass flow rate m dot is equal to mass, that's m, all over time, that's t. Right? So at this point here, let's get the SI unit for mass flow rate. Mass is measured in kilogram, as we all know. Time is measured in seconds. So it means that the SI unit for mass flow rate is simply kilogram per seconds. When it comes to fluid mechanics, SI units are confusing. So I'll take my time to explain and break down SI unit for you. So when you say kilogram per seconds, that's what the mass flow rate, please. Mass flow rate. All right, I haven't discussed the definition of mass flow rate and the mathematical expression of mass flow rate. Right, at this point, let's take some example to further explain the concept behind mass flow rate before we move to discharge, or perhaps we call it volume flow rate. example 1 says an empty cup weighs 5 kilograms. After 10 seconds of collecting water, the cup weighs 15 kilograms. What is the mass flow rate? Let's get this done, please. First, in science, our first task is to what? List out the given parametric units. Solution, example 1. Solution, what are we given? So my given, first, I'm told that an empty cup weighs 5 kilograms. That's my mass. The first mass I'm given is what? 5 kilograms. Next up, after 10 seconds, so the time taken, t, time, which is small t, is what? 10 seconds. Mass, that's m. Let me just call it m. That's 5 kilograms. Proceeding from here, of collection of water, the cup weigh, after collecting water, the cup weighs 15 kilograms. I'm given second mass. So let me call this on M1. Let me call this M2 as what? 15 kilograms. What is the mass flow rate? So what is M dot? So I'm looking for what? M dot. What we know before now is that M dot, recall that what we know before now is that mass flow rate M dot is equal to total mass all over time. But in this question here, I'm giving two masses. How can I get my total mass? So your total mass, from here, total mass becomes, since I'm giving two mass, to get my total mass, I'll do M2 minus M1. That will give me total mass all over my time t. At this point here, mass flow rate M dot is equal to M2, that's 15, minus M1, that's 5. 15 minus 5 divided by time. What's my time there? 10. So at this point, I'll have 10 all over 10, which will give 1 watt. This is mass flow rate. 1 watt, 1 kilogram per second. Note that the S sign for mass flow rate is simply what? The kilogram per second. So that becomes my answer to that question. Let's take example 2. Example 2 says if the mass flow rate of a fluid is 12 kilograms, so mass flow rate, that's M dot. So example 2, let me just read the question first. If the mass flow rate of a fluid is 12 kilograms per second, how long will it take to fill a container with 52 kilograms of fluid? So for this, I'm given mass flow rate, that's M dot, as what there? As 12 kilograms per second. Observe, kilogram per second. Kilogram per second represents your mass flow rate. All right, next up, I'm given that how long will it take? So it means I'm looking for time. How long will it take? That's time. T is unknown. All right, I'm giving weight there. That's weight 52. Mass, I'm giving mass there, M, as 52 kilograms. So let's get what's it called? Let's get our time. Yeah. Recall that we established earlier that mass flow rate M dot is equal to mass all over time. I'm looking for time, yeah. So I know mass as 52. I know my mass flow rate as 12. So put in value 12. This 12 here, 12 is equal to mass. That's 52 all over time. Multiply, or perhaps cross multiply, that becomes 12t is equal to 52. Divide by 12, divide by 12. So it means that therefore the time taken is equal in value to, if I divide 52 by, what's it called? If I divide 52 by 12, Divide 52 by 12. 52 divided by 12, I will have about 4.3. So my answer then becomes 4.3 seconds. So this becomes how to solve this problem here under the concept of mass flow rate. All right, let's discuss second part there called volume flow rate. Welcome back. Let's discuss second part type of flow rate called volume flow rate. Number 2 there is called volume flow rate. Let's discuss volume flow rate. By definition, volume flow rate is simply the rate at which total quantity of volume of fluid flows out in a particle at a particular time, or perhaps you can just say volume flow rate is simply the ratio of volume to time, right? So also note that volume flow rate is also called discharge. All right, volume flow rate, important please, also called discharge. So the symbolic representation for volume flow rate becomes Q. We use Q to represent volume flow rate. Now at this point, don't be confused. Why is it that mass flow rate was m dot? So Q becomes the symbolic representation for volume flow rate. Now at this point, some of you might be asking that why is it that mass flow rate was m dot? Now I'm having volume flow rate, that should be v dot too now. So why is volume flow rate now Q? Why is it not v dot? Here's the idea, please. Look up, please. Here's the idea. In in science, whenever any parameter has a dot on its head, that is m dot, it means that that parameter is changing with respect to time. So having m dot represents what? Mass all over time. That's all. So in science, there's already a parameter that represents v. That's velocity. So I'm saying v dot now. This one now is velocity all over time. This one becomes velocity over time, v dot. So now if you're telling me that v dot is volume flow rate, you are wrong. Why? Because you are telling me that v dot now from here is acceleration. What's the formula for acceleration? Velocity over time. That's acceleration. So v dot represents what? Acceleration, not what? Volume flow rate, please. So it means that volume flow rate is represented what? With Q. Why not v dot? I just explained. V dot represents what? The acceleration. Alright, at this point here, well, let's get a particular expression for discharge of perhaps volume flow rate. Mathematically, volume flow rate, that discharge Q, is equal to total volume all over time. At this point here, note that the mathematical expression for discharge is given as volume all over time. Let's get SI in place. What we know before now is that volume is measured in meter cube, time in second. So hence the SI unit for what's it called, discharge, or perhaps we want to volume flow rate, is what there is meter cube per second. So the SI unit for discharge is simply what's it called, meter cube per seconds. At this point, note something please. Note something please at this point. Note that discharge can also be expressed as the product of, note that discharge can also be expressed as the product of area times velocity. So at this point, I'm telling you now that discharge Q can also be expressed as area times velocity. Proof. Let's prove this. Let's prove that. Why is it? What we know is that this charge is volume over time. How come can we still express this charge as area times velocity? Proof. Let's prove it, please. Let's prove this one. Please. Alright, when it comes to proving this man here, why is it that this charge Q is area times velocity? Let's prove, please. What we know initially was that this charge Q was equal to what? Volume over time. True or false? True. From your math idea, what's formula for volume? Volume is what? Length times breadth times height. True or false? True. All over what? This time here, T. Observe, please. Oh. Now this charge now Q is now equal to, I'll separate something. What and what? Observe, please. I'll take length and breadth together. Length times breadth into H over T. This is still correct. Length times breadth times height is length, breadth, height all over this time. See, correct, but different in expression, please. See, correct, the same thing, but different in arrangement, or perhaps yes, that's arrangement. At this point here, what do we know? Length is measured in meters. Breadth is also measured in what? Is a meter. They are both length in meters. So Q now is equal to, this is in meters. Multiply, this is what? In meters too now. So into H is an height, also measured in what? In meters all over time in what? In second. Observe, please. Oh. At this point, this charge Q is equal to meter times meter will give meter squared into meter over second. Observe. Oh. Now in science, when you hear the word meter squared, what comes to mind? Area comes to mind. So Q now is equal to area times, there's a kind of formula that expresses, there's a kind of formula that has its SI unit as meter per second. That's what? Velocity, right? Velocity is better than what? Meter per second, or perhaps either you call it speed or velocity. They are both measured in what? In meter per second. So this becomes what? The velocity. So I'm saying that Q, this charge now, is equal to area times velocity, as I proved to it to you, as you can see in front of you. So this charge can be expressed in two ways, either what? Volume over time, or area times velocity. At this point, we will start solving problem under this charge. Let's look into something called relationship between discharge and mass flow rate. Very interesting. Let's discuss relationship between discharge and mass flow rate. What simple relationship between discharge and mass flow rate? Someone told me that, how come is there relationship in science? How come are you doing boyfriend and girlfriend in science? No, there's nothing like boyfriend and girlfriend in science, but at least you should know what is common, what is similar between parameter in science. So let's call relationship between what's it called, mass flow rate and volume flow rate. Alright, let's discuss relationship between discharge and mass flow rate. Don't forget, see discharge also called volume flow rate. Oh, please. Alright, what's the relationship? At this point here, note something please. Let's the relationship. What we know before now is that this charge Q is equal to what? Volume over time. True or false? True. What we know before now. This charge, volume over time, as we said earlier now. At this point, also, with respect to density, mass density rho is equal to what? Mass all over volume. Don't forget this in our first class of fluid mechanics. We established this concept, mass density, right? Swap these two. V is equal to m over rho. Swap these two. So I want V here, then rho here. So call this one here, call it equation 1. Call this one, call it equation 2. Put equation 2 into 1. Put 2 into 1. Let me call it 2. Let me use figure. This is 1. So put 2 into 1. I'll have that this charge Q is equal to V. What's V? M over rho. So mass over rho as my V all over T. This time here, T. At this point, what next? Your next task now is to observe that I will apply the concept of reciprocal here. So from this point now, this charge Q is equal to mass all over rho. Mass all over rho divided by what? Time. Time. At this point, let's get this right. Q now, this charge Q is equal to mass all over rho times what? Invisible one here. 1 comes first all over this time. So I'm saying that this charge now Q I'm saying this charge Q now is equal to mass times 1. Sorry, that's mass all over rho times time. Give rho and time. I will separate something. What and what? Observe that this charge Q now is equal to m over t times 1 over rho. 1 times mass will give mass. Rho times t will give rho t, or t times rho will give rho t. The same thing here. So they are still the same thing. What? Different in arrangement. This one and this are the same thing, but what? Different in arrangement. This man here and this one are the same thing, but what? Different in arrangement. Just correct. At this point, recall that we said m dot is equal to what? Mass all over time. True or false? True. And I'm seeing m dot here too. Mass over time. So replace mass over time with what? M dot. So Q now is equal to m dot. Why is it m dot? Because I'm having mass over time. Mass over time, that's m dot. So m dot times 1 over rho. From here, multiply through m dot times 1 will give m dot all over rho. So it means that this charge Q now is equal to m dot divided by rho. Let's get this right, please. Let's get this right. From here now, this charge Q now is equal to mass all over rho, mass flow rate all over rho. Multiply these two, I'll have that this charge rho is equal to mass flow rate. So therefore, mass flow rate can be expressed as the product of this charge and mass density. A very important relationship you need to note when it comes to discharge and mass flow rate. For an overview, now look up. For an overview, I gave you 4 formulas now. When it comes to mass flow rate, we said mass flow rate is what? Mass all over time. That's the first one. When it comes to mass flow rate again, Mass flow rate can be expressed as what? The product of discharge and what? Mass density. That's the first one. When it comes to discharge can be expressed as what? The product of what? Area, that's volume all over time. That's the first one I gave you for discharge. Also for discharge now, can still be expressed as what? Product of area and velocity. So these are like the four formulas you need to be familiar with when it comes to concept of flow rate, right? As you can see what we are having there. All right, at this point here, let's use all this technique, idea and system to solve some problems, and let's see what we get. All right, before we dive into solving problems, let's note something, please. Let's understand one technique. What's technique? Observe something, please. S is used to measure time in second, right? M is meter, right? As we know, M/S, this is what? Either you call it velocity or what? Or speed. M/x squared, this is what? Kinematic viscosity. This kind of, so next up, M²/x, this is what? Acceleration. Next up, M³/s, this is what? Discharge. Observe the ranging. Time, length in meter per second, that's what? Velocity or call it speed. This is what? Acceleration. This is what? Kinematic viscosity. This is what? Acceleration. This is called acceleration. This is called kinematic viscosity, and this is called discharge, please. Meter per second squared, acceleration, please. This is called kinematic viscosity, which was discussed in the last class, and this is called discharge. Observe the ranging. The more we continue in our study of fluid mechanics, the more we had more units, let's say SI units. All right, let's solve some problem and let's end the concept of flow rate. Welcome back. Let's solve this problem here. Example 1. A liquid of specific gravity 0.52 flow at a rate of 0.3 meter cube per second. Find its mass flow rate. Let's get this done. So solution, first task, write out the givens. So I'm given that a specific gravity of 0.52. So specific gravity Fg, that's 0.52. Flow at a rate of 0.3 meter cube per second. So I'm having 0.3 meter cube per second. This is what? This discharge. So discharge. So I'm given discharge Q as 0.3 meter cube per second. Find its mass flow rate. So looking for what? M dot. So mass flow rate M dot. Observe that for this mass flow rate here, I'm having discharge. So I'll not even try to recall that mass flow rate is equal to M over V. This will be wrong, because I still gave an expression for mass flow rate as what? Q times rho. True or false? So I'm having Q here, so I'll record this one here. So record that mass flow rate M dot is simply the product of discharge and mass density, which is rho. So we need two things: discharge, which is given, mass density is not given. So let's get mass density. We recall before now in our first class for fluid mechanics, we said that what's it called? Rho, which is mass density, is equal to what? Specific gravity times 1000. We said this last class of fluid mechanics when I did introduction. So rho here is equal to specific gravity is 0.52 times 1000. So my mass density is what? 520 kilogram per meter cube as the value for my mass density. At this point here, let's get this right. M dot now, which is my mass flow rate, is equal to discharge times what there? Rho. Mass flow rate M dot is now equal to what's discharge, please? 0.3 times 520. So M dot now is equal to 156 kilogram per second. So my value for this question becomes 156 kilogram per second. All right, before we end this concept, note something, please. Note something, please. Note that for a fluid flow with different velocity, the discharge Q is area times mean velocity. So if you're having what's it called, a fluid flow with different velocity, right? When a fluid is flowing with different velocity, it means that the discharge there becomes area times what? Not just velocity, but what? The main velocity. All right, see you in our next class of fluid mechanics.